Imagine you're standing on the factory floor of a massive industrial plant. You're looking at your spreadsheets,
Yeah.
your profit and loss statements,
Right.
and you have this massive operating budget, millions upon millions of dollars,
Mm.
but you're just hemorrhaging money on catastrophic equipment failures, missed shipments, and staggering scrap rates.
It's a nightmare scenario. Yeah.
It really is. But what if I told you that this culprit, the silent assassin, tearing your machines apart, accounts for, like, less than 2% of your operating budget?
Honestly, it's the kind of hidden metric that keeps a chief operating officer awake at night. When you frame it like that, it almost sounds like an accounting error. Right?
Yeah, exactly.
Because how can something so financially insignificant on a balance sheet be responsible for up to 70% of a factory's mechanical destruction?
Right. You would instinctively think a 7% failure rate has to come from the most expensive, highly monitored, complex component in the building, like the main processor or something.
Or the heavy steel framework.
Exactly. But it doesn't. So today's deep dive is into a multi-million-dollar blind spot inside heavy industry. Specifically, we're looking at the world of plastic injection molding and the absolute havoc caused by hydraulic fluid degradation.
It's such a critical topic because it really forces us to dismantle our basic assumptions about maintenance and engineering and, well, capital preservation in general. We're looking at a scenario where the standard protocols, the very checklists we've been taught to trust for decades, are actively providing a false sense of security.
Yeah, exactly. So here is our mission for you today. If you're a plant manager, a COO, an engineer, or even if you're just someone fascinated by how incredibly complex systems fail from the inside out, you need to hear this.
You really do.
We're going to unpack the actual physics of how these massive machines break down. We're going to understand the chemistry of exactly why your standard by-the-book maintenance is, frankly, completely blind to the threat.
Totally blind.
We're going to expose a hidden industry bottleneck created by the machine manufacturers themselves. And finally, we'll outline a complete actionable transition from a reactive nightmare of emergency repairs to a proactive oil health strategy.
And that transition, I mean, it is the only way forward. Right now, the manufacturing industry is bleeding capital through a microscopic oversight. We really have to move past treating the symptoms. We have to cure the underlying disease.
Okay, let's unpack this.
Yeah.
We have to start by setting the scene on the factory floor. Injection molding. For those who aren't, walking a production line every day, these machines are the beating heart of global manufacturing.
Whoa, absolutely. They make everything.
Yeah, they create everything from precision medical syringes to the dashboard of your car. And the way they do it is incredibly violent.
It's massive force.
Right. They take molten polymer, heat it to hundreds of degrees, and just force it into a heavy steel mold under immense physical pressure.
And to execute that violent process successfully, they demand absolute, uncompromising systemic consistency. You're dealing with fluid dynamics, molten plastics, and incredibly tight dimensional tolerances.
Like fraction of a millimeter tight.
Exactly. If the injection pressure fluctuates by even a fraction of a percent, or if the timing is off by milliseconds, the part is completely ruined. And the critical medium transferring all of that force and the muscle of the entire operation is the hydraulic oil.
So the oil is the power transmitter. That makes intuitive sense. But over the last decade, a major architectural shift happened in this industry. The original equipment manufacturers, the OEMs who design and build these massive machines, they decided to start shrinking the hydraulic fluid reservoirs.
They did.
And we're not talking about shaving off a few gallons here. They shrunk these reservoirs by up to 40%.
Right. And if we look at the historical context, the motivation behind that design change is purely driven by market economics.
Money, basically.
Exactly. I mean, what actually sells a machine to a factory? OEMs know that floor space in a manufacturing plant is premium real estate. Every single square foot has a dollar value attached to it.
Oh, for sure.
If an OEM can engineer a machine that takes up 30% less square footage but promises the exact same or even faster cycle times, they win the contract. On paper, to a procurement officer, these machines look like a massive leap forward in operational efficiency.
But wait, physics always collects its toll.
Yeah.
You can't just magically delete 40% of the fluid volume from a high-pressure system and expect the underlying thermodynamics to remain identical.
No, you absolutely cannot.
So it's like trying to cool a high-performance race car engine using only a teacup of coolant. The fluid simply never gets a chance to exhale before it's subjected to intense heat and pressure all over again.
That's a great analogy. Because it's a closed-loop hydraulic system, the fluid can't escape. The better way to look at it is through the lens of thermal recovery. You have the exact same amount of work being done, the same immense pressure generation, the same rapid cycle times, the exact same friction.
But less oil.
Exactly, but now you have significantly less hydraulic oil to absorb and dissipate that energy.
So the thermal burden per gallon of oil has just skyrocketed.
Completely skyrocketed. In a traditional, older machine with a massive reservoir, the oil completes a high-pressure cycle, returns to the large tank, and essentially gets a break. It has time to sit.
It exhales.
Right. It releases the intense heat into the ambient air, it releases entrained air bubbles, and it cools down before the pump sucks it back into the high-pressure zone. But by shrinking a reservoir by 40%, the OEMs drastically reduce that recovery time.
So it's just constantly working.
The oil is now subjected to almost constant, relentless thermal and oxidative stress.
And that stress forces a chemical change, right? The intense, repetitive heat literally cooks the oil. It causes the hydrocarbon molecules to break down, oxidize, and form a very specific type of contaminant. Mechanical engineers call this varnish.
Varnish, yes. And we have to be very precise about what varnish actually is. It sounds almost benign, like a wood finish.
Like I'm painting my deck.
You're right. But in a highly engineered hydraulic system, it is catastrophic. We must understand that this isn't external dirt. This isn't metal shavings grinding off a gear. This is the hydraulic oil itself chemically degrading.
It's turning into something else.
Yes, it polymerizes, turning into a completely different substance, a sub-micron oxidative deposit.
And when you say sub-micron, we were talking about a particle so unimaginably tiny, it's smaller than a red blood cell.
Yeah.
But the most insidious aspect of this varnish is how it behaves at different temperatures. There's this phenomenon called the temperature paradox.
This is the exact mechanism of the failure, and it dictates everything that goes wrong. Varnish has a unique, almost deceptive relationship with temperature regarding its solubility.
Okay, how so?
Well, when the hydraulic oil is extremely hot, which it is when it's under high pressure inside the pumps and the working components, the varnish remains completely soluble. It dissolves entirely into the base oil.
Wait, really?
Yeah, you cannot see it. If you look at the fluid, it appears perfectly clear.
Wait, stop right there. You're saying the varnish dissolves when it's hot? That makes zero sense to me.
I know, it sounds counterintuitive.
Because usually when things get hot in a machine, they burn, they char, they turn into a solid crust, like food baking onto the bottom of an oven. Why is this oil doing the exact opposite?
It all comes down to kinetic energy and molecular bonds. Think about dissolving salt in water. Cold water holds very little salt before the salt just piles up at the bottom of the glass. But if you boil that water, the kinetic energy of the water molecules increases drastically. They move faster, creating space, and they can break apart and hold significantly more salt molecules in suspension.
Ah, okay, I see.
The hot hydraulic oil acts the exact same way. The extreme heat and agitation keep the oxidized varnish molecules fully dissolved in a liquid state.
Okay, I follow the kinetic energy part. But eventually, the oil has to leave the hot zone. It doesn't stay in the pump forever.
Precisely. And this is where the paradox becomes a crisis. When that hot oil cycles out of the high-pressure pump and hits the cooler areas of the system, the valves, the steel lines running along the exterior, the narrower passageways, the fluid's temperature drops rapidly.
Kinetic energy falls.
Yes. The oil can no longer hold those oxidized molecules in suspension, so they precipitate out. They transition from a dissolved liquid state into a hard, sticky, solid resin, and they aggressively coat the first metal surface they touch.
So it's less like a typical mechanical breakdown and more like pouring liquid epoxy into a Swiss watch. As long as the epoxy is hot, it flows and the gears turn. But the second it hits room temperature, the whole thing seizes into a solid block of resin.
That is a highly accurate way to visualize it. We have to stop viewing hydraulic fluid merely as a slippery liquid that prevents friction.
Right. It's more than that.
It is a thermodynamic component. It has rigid physical and chemical limits. By shrinking these reservoirs to save floor space, the OEMs push the fluid past its thermodynamic breaking point.
Okay, so we've established the chemistry. We have this sticky sub-micron epoxy precipitating out of the oil and coating the cooler zones of the machine. But how does this microscopic chemical breakdown manifest as massive physical destruction on the factory floor?
It's a direct chain reaction.
Because a hot reservoir sounds like a theoretical engineering problem, but a 70% failure rate is a very real, very fast financial disaster.
Right. And the bridge between the microscopic chemistry and the macroscopic disaster is found in the most delicate, critical components of the entire machine, the proportional servo valves.
The servo valves?
Yes. These valves are the absolute brains of the hydraulic system. They dictate exactly how much pressure is applied and exactly when it is applied to move those massive steel molds and inject the plastic.
And these servo valves are not blunt instruments, right? They operate with incredibly tight clearances.
Extremely tight. We're talking about internal clearances measured in mere microns. The metal spools inside these valves have to slide back and forth with near zero resistance to maintain the rapid split-second cycle times required by modern manufacturing.
So what happens when that hot oil carrying the dissolved varnish enters the intricate pathways of the servo valve and cools down by just a few degrees?
The varnish precipitates directly onto the internal surfaces of the valve. It coats the spool and the housing in a microscopic layer of sticky resin.
Wow.
So now, instead of two pristine, polished metal surfaces gliding seamlessly past each other on a microscopic film of oil, you have sticky, resin-coated surfaces dragging against each other. This creates a massive, unpredictable spike in internal mechanical friction.
And the engineering term for this erratic behavior is valve hysteresis and chatter,
Yes.
right?
Yes, exactly. Hysteresis fundamentally means there is a lag between a command and an action. The machine's central computer sends an electrical current to the valve, commanding it to open to a very precise position to deliver, say, 150 megapascals of pressure.
Okay.
But because of the sticky varnish, the valve resists. It binds up.
Stuck in the resin.
Exactly. So the computer sends more current to push harder.
Yeah.
Then suddenly the static friction breaks and the valve shoots violently past the target position. That erratic, jerky, overcorrecting movement is the chatter.
So the valve is literally stuttering, and the injection pressures are fluctuating wildly. How does that erratic pressure translate to the actual physical plastic part being molded? Let's connect this dirty oil directly to the specific defects that pile up in the scrap bin. Let's start with short shots.
Sure. A short shot is exactly what it sounds like. The molten plastic does not completely fill the precise geometry of the mold cavity.
Why not?
This occurs because the sticking servo valve causes a sudden, momentary drop in injection pressure. The machine simply fails to push the highly viscous plastic hard enough or fast enough to reach the furthest edges of the mold before the plastic begins to cool and solidify. You end up with a partially formed, structurally useless part.
And if you're making something critical, like a medical device component, a short shot means the entire batch is compromised. Next defect on the list is flash. That sounds like the inverse of a short shot.
It is the exact inverse. Flash occurs when the sticky valve fails to properly control the clamping force that holds the mold shut, or it overshoots the injection pressure, overpacking the mold.
So too much pressure.
Way too much. It pushes too much molten plastic too violently. The excess material is forced out of the cavity and escapes along the parting lines, those microscopic seams where the two halves of the steel mold meet.
So the part is ejected, looking like it has these thin, ragged plastic wings on the edges.
Correct. And while a short shot is purely a material loss, flash introduces a devastating labor cost.
Because someone has to fix it.
Exactly. You now have to pay a human technician to sit at a workstation with a blade and manually trim the excess plastic off every single part to bring it back into dimensional tolerance. It absolutely annihilates your production efficiency.
Man, that's brutal. Then we have sink marks and voids.
These are particularly dangerous because they aren't always immediately visible to quality control. Sink marks are physical depressions on the surface of the part, and voids are internal air pockets or vacuum bubbles.
What causes them?
They're caused by inconsistent packing pressure and uneven cooling. If the varnished servo valve cannot maintain a perfectly steady holding pressure while the plastic cools and shrinks inside the mold, the material pulls away from the exterior surface, creating a sink mark.
Oh, I see.
Or it tears internally as it shrinks, creating a void. This completely compromises the load-bearing integrity of the final part.
The technical documentation also mentions burn marks. I would assume that's just the plastic getting too hot in the barrel.
It's related, but it's driven by the valve. Burn marks are dark, carbonized discolorations. They happen when the system loses control of the injection speed again, controlled by the chattering valve.
Too fast.
Yes. If the plastic is injected too rapidly, it can superheat the trapped gases inside the microscopic vents of the mold through rapid compression. The gas gets so hot, it literally scorches the advancing front of the molten polymer.
Dieseling, like a piston compressing gas until it combusts.
Precisely.
And finally, we have warping.
Warping is when the final part twists, bows, or bends out of shape after it is ejected and cools down. This happens due to uneven internal shrinkage.
And the valve is doing that too.
Indirectly, yes. That shrinkage is directly tied to unbalanced material flow and wildly inconsistent pressure during the injection phase. Again, all roads lead back to the erratic, unpredictable performance of the varnished servo valves.
So we're looking at a microscopic chemical reaction in the hydraulic tank directly causing deformed parts, wasted resin, and intense manual labor.
This is how Varnish quietly, systematically destroys overall equipment effectiveness, or OEE.
An OEE is basically the holy grail metric.
Right. It is the gold standard metric for manufacturing profitability. It measures availability, performance, and quality. When you are tossing parts in the scrap bin because of short shots or flash, you aren't just losing raw plastic.
You're losing time.
You're losing the expensive machine time it took to mold that bad part. You are paying for increased manual inspection labor to sift through the batches. And ultimately, you are missing delivery deadlines for your clients.
Okay, I have to challenge this logic for a second.
Sure, go ahead.
If I am a machine operator on the floor, and my parts are coming out deformed, say I'm getting a bunch of short shots, I am not going to blame the hydraulic oil in the basement. I'm going to walk over to the digital control panel, look at the injection pressure parameter, and I'm just going to bump it up.
Naturally.
Right. If the machine isn't pushing hard enough, I'll tell it to push harder. Why wouldn't a technician just adjust the machine settings instead of blaming the oil?
Because you are fighting chemistry with software. It is a very common reaction, and it is exactly why this problem escalates into a catastrophic failure. When a technician adjusts the machine settings to compensate for a sticking valve, they are engaging in a dangerous practice called process drift.
Process drift. Drifting away from the engineered baseline.
Precisely. You increase the pressure parameter on the computer by 5% to overcome the physical-mechanical resistance of the sticky varnish inside the valve.
And it works. Right.
And for a little while, it seems to work. The short shots disappear, but the varnish hasn't gone away. The thermal degradation is still happening, and the resin is still accumulating. So 2 weeks later, the valve sticks worse.
Oh, man.
The technician walks over and bumps the pressure up another 5%. You are constantly chasing the process, adjusting digital parameters to mask a physical root cause.
Until you max out the machine.
Exactly. You drift the process parameters so far out of optimal specification that the machine is now running violently at absolute maximum hydraulic capacity just to force the sticky valve to produce a normal part.
That sounds like a recipe for disaster.
The internal stresses on the pumps and hoses become immense, and eventually the varnish buildup becomes so severe that the mechanical friction overcomes the maximum hydraulic force. The valve completely seizes. The machine shuts down entirely. By masking the symptom, you guarantee the catastrophic destruction of the component.
So adjusting the dials is just a temporary Band-Aid on a bullet wound. But let's zoom out and look at the business side of this, because there is a really fascinating perspective on who actually benefits from this cycle of destruction. We can call it the quiet architect perspective.
This requires us to engage in some first principles thinking and examine the control points within the heavy machinery industry. Who owns the architecture of the machine?
The original equipment manufacturers.
The OEMs.
The exact same people who decided to shrink the reservoirs by 40% to sell a smaller footprint.
Precisely. They control the fundamental design. Now, we have to ask the critical business question, who wins financially when this failure cycle occurs?
The OEM, obviously.
The OEM wins on the front end by advertising a smaller, faster machine. That gets them the initial multi-million-dollar capital expenditure contract. But they also win massively on the back end.
Because things break.
Right. When that shrunken reservoir inevitably thermal stresses the oil, generates varnish, and destroys those highly sensitive servo valves, who do you have to buy the replacement valves from?
You have to buy them from the OEM.
Yes. The opacity of this fluid degradation, the fact that it's invisible to the naked eye, hidden inside steel pipes and hard to diagnose, actually protects and fuels the OEM's recurring revenue stream.
It's a trap.
They profit twice. They sell you the structurally compromised machine, and then they sell you the exorbitant proprietary replacement parts when the machine inevitably cannibalizes itself due to their original architectural design choices.
Here's where it gets really interesting. You are framing this almost like a hostage situation. The factory is bleeding capital through a microscopic oversight, and they're paying their captors a ransom for the privilege.
It's a harsh way to put it, but mechanically it's accurate.
But why does the plant manager or the chief operating officer allow this to happen? If 70% of their downtime is tied to the fluid, why isn't the fluid the most fiercely protected asset in the building?
It comes down to corporate psychology and traditional accounting structures. Historically, hydraulic oil represents less than 2% of a manufacturing plant's total operating budget.
It's tiny.
It is psychologically categorized as a cheap, dirty consumable, a commodity, like paper towels or light bulbs. When an executive looks at a massive P&L spreadsheet, they do not see the oil as a critical structural component. They see it as a rounding error.
So because it's cheap, they absorb the cost of emergency valve replacements and scrap as a normal business expense.
They ignore the root cause, yes. When a servo valve seizes and halts production, they write a $10,000 purchase order for a new valve, pay for emergency overnight shipping, and write it off as routine maintenance.
Unbelievable.
They accept double-digit scrap rates and delayed shipments as just the unavoidable friction of doing business in heavy manufacturing. They are treating the symptoms at staggering expense because curing the disease requires a fundamental paradigm shift in how they view the machinery.
Well, we need to give these executives a rock-solid business case to force that paradigm shift. We need the metrics to justify taking that maintenance budget, shifting it away from emergency replacement parts, and focusing it entirely on the oil.
The metrics exist, and they are powerful.
What are the actual numbers if a plant successfully transitions to proactive oil health?
The return on investment is staggering, and it immediately hits the bottom line. By deploying proactive restorative engineering solutions to purify the oil, which we will break down the chemistry of shortly, a plant can extend the life of their hydraulic fluid up to 100,000 hours.
Wait, 100,000 hours. That's like over a decade of continuous 247 operation on the exact same fluid.
It is transformative. You stop replacing the fluid. Furthermore, it reduces the consumption of new virgin replacement oil by 95%.
So you're barely buying new oil.
You are no longer paying to dispose of thousands of gallons of hazardous degraded oil into the waste stream, and you are no longer buying expensive new stock to replace it. But the most critical metric for the executive team is this: a proactive oil strategy drops overall equipment downtime by 70%.
A 70% reduction in machine downtime. That is the metric that changes the profit margin of the entire corporation.
It dictates market dominance, but achieving it requires critical thinking from leadership. We must stop treating hydraulic fluid as a disposable commodity. We have to start engineering it, monitoring it, and maintaining it as a core structural asset of the machine, just as vital as the steel frame or the digital processor.
If the oil fails, the factory fails.
Exactly.
But wait, this brings up a huge contradiction that I can't wrap my head around. Every factory I have ever visited has strict maintenance protocols. They have giant filters on these machines. Technicians are constantly pulling oil samples on little plastic bottles and sending them off to laboratories for analysis.
Look, they test constantly.
Right. If this varnish is such a massive, expensive problem, why aren't standard by-the-book maintenance routines catching it before the valves explode? If I am paying a certified lab to analyze my oil, why am I still having machines lock up?
Because the standard defenses your technicians are using are fundamentally flawed for this specific chemical threat. You are trying to fight a modern sub-micron chemical war using medieval mechanical weapons. Let's start with your first line of defense: mechanical filtration.
The physical filters installed on the machine itself.
Right. Standard mechanical filters use physical barriers, essentially a tightly woven mesh, fiberglass, or a pleated paper element with microscopic holes to catch dirt, metal shavings, and environmental debris.
Okay, that makes sense.
They work on the basic principle of size exclusion. They trap particles that are physically larger than the holes in the filter media.
But we established in the beginning that varnish is sub-micron. It is unimaginably small.
Exactly. The varnish particles, even when solid, are smaller than the smallest pores in standard mechanical filters. They slip right through the fiberglass barrier without even grazing the sides.
They just bypass it.
But the failure of mechanical filtration is actually much worse than that. Remember the temperature paradox we discussed?
Oh, right. The kinetic energy. The varnish is completely soluble when the oil is hot. It dissolves into the liquid.
Yes. And where are the mechanical filters traditionally located in the architecture of the machine? They are installed in the high-pressure, high-temperature return lines to protect the pump.
Oh, no.
Exactly. So when the hot fluid passes through the filter, the varnish isn't even a solid particle yet. It is fully dissolved in the liquid state. You cannot filter a dissolved liquid with a physical net.
The varnish completely bypasses the physical filtration system as a liquid.
And then precipitates into a solid resin later. When it hits the cooler servo valves, it renders the filters entirely useless.
Okay, so the mechanical filters are literally blind to the threat. But what about the oil analysis? Every plant manager has a binder full of lab reports on their desk. We have a very specific real-world case study to look at here. Machine 15.
Machine 15, a classic example.
This was a large plastic injection molding machine using AW46 hydraulic oil. The plant manager was experiencing severe performance issues, massive scrap rates from short shots, so he did the responsible thing. He increased the frequency of his standard oil analysis.
And what did the laboratory reports tell him?
The reports came back completely acceptable. They were greenlit, but the machine still failed catastrophically, and when the technicians opened it up, the servo valves were entirely caked in hard varnish.
A total failure.
So if I'm paying for an oil analysis report and it comes back green, you're telling me I'm still driving off a cliff at full speed.
Yes, because you are staring at the wrong dashboard. The fundamental problem with traditional oil analysis is that it was designed decades ago to look for entirely different failure modes like water contamination or massive metal wear.
Not varnish.
Testing for the wrong failure mode is infinitely worse than not testing at all because it provides that false sense of security. You think you are completely safe, so you consciously ignore the physical symptoms, the process drift, of the machine.
We need to break down exactly why these traditional tests fail so spectacularly to catch varnish. The first standard test the lab runs is elemental spectroscopy. Now, I know this test is used to look for specific metals in the oil. It tells you if your steel gears or copper bearings are wearing down by counting the metal atoms.
Correct.
But it's also used to measure the chemical additives in the oil, right? Specifically something called ZDDP.
Yes. ZDDP, zinc dilcolldithiophosphate. It is the dominant anti-wear additive used in almost all industrial hydraulic oils. It is absolutely crucial.
What does it actually do?
Under high heat and pressure, the ZDDP molecule decomposes and reacts with the steel, forming a sacrificial microscopic glass-like layer on the metal parts to prevent them from grinding against each other. Elemental spectroscopy is highly effective at identifying the raw zinc and the phosphorus atoms floating in the oil sample.
So if the spectroscopy report says my zinc levels are perfectly fine, why is the machine failing from wear and friction?
Because elemental spectroscopy is incredibly literal. It only counts the raw atoms. It does not measure the structural health of the complex molecule.
Oh, I see.
Under the extreme thermal stress of that shrunken reservoir, the complex ZDDP molecule is physically sheared and thermally broken apart. It degrades into useless, inert sulfates and phosphates. It no longer provides any anti-wear protection whatsoever.
But the atoms are still there.
However, the raw elemental atoms, the zinc and the phosphorus, are still physically present, floating aimlessly in the degraded oil. The spectrometer sees the raw atoms and reports back, "You have plenty of zinc."
Wow.
It cannot differentiate between a fully functional ZDDP molecule and the shattered remains of a dead molecule that is actually actively contributing to the sludge and varnish.
That is insane. It's like a building inspector counting the scattered bricks of a collapsed house on the ground and reporting, yep, all the bricks are here, the house is in perfect condition.
That is a phenomenal way to understand it. The test counts the pieces, not the structure.
Okay, what's next?
The second standard test labs rely on is the acid number. The logic is that as oil oxidizes and breaks down, the final chemical byproduct of that oxidation is acid. So traditionally, if the acid number spikes on the report, you know your oil is highly degraded.
But I'm guessing that doesn't work for modern hydraulic systems either. Why do modern oils hide the acid?
It comes down to how lubricants are manufactured today. To combat these high-stress environments, lubricant manufacturers shifted away from older Group I oils to highly refined Group 2 and Group 3 base oils.
What's the difference?
These newer oils are heavily hydrocracked at the refinery.
Hydrocracked, meaning they break the molecules with hydrogen.
Exactly. They saturate the molecules with hydrogen under extreme pressure to remove impurities like sulfur and polar aromatics. This makes the base oil incredibly stable and resistant to oxidation.
Sounds like a good thing.
It is, mostly, but it introduces a fatal flaw. It gives the oil very low solubility. Because the polar molecules were removed at the refinery, the oil can no longer dissolve or hold on to its own degradation products.
Wait, I'm losing the thread. What does the solubility of the oil have to do with the acid test?
Everything. Because the Group 2 oil has such low solubility, the moment the oil begins to degrade and form intermediate oxidation products, the precursors to acid those products immediately drop out of suspension.
Oh, they don't stay in the oil.
They literally fall out of the oil and stick to your valves as varnish before they can fully convert into an acidic molecule that the test can actually read. Furthermore, acids only begin to form after the primary and secondary antioxidants in the oil are completely depleted.
So by the time the acid number finally spikes in the lab report, wait, I shouldn't say that. By the time the acid number spikes, it's already too late.
It is entirely too late. The oil has been completely unprotected and degrading for weeks or months. The intermediate products have already dropped out, and the varnish is already fused to your servo valves. The acid number is a massive lagging indicator. It essentially tells you that the battle was lost a long time ago.
And the final traditional test we rely on is viscosity, measuring the thickness or the flow resistance of the oil.
It suffers from the exact same temporal problem. Severe oxidation and polymerization will eventually cause the oil to thicken, and the bulk viscosity will increase.
But let me guess, lagging indicator.
Exactly. By the time you see a measurable change in the bulk viscosity of hundreds of gallons of fluid, the microscopic, localized varnish damage to the micron clearances of the servo valves is already complete.
So if standard filters and standard tests don't work, what is the actual solution? Your mechanical filters are completely blind to the dissolved thread, and your standard oil analysis actively lies to you by counting broken molecules and measuring lagging indicators.
It's a terrifying picture, yes.
If I am the COO, I am panicking.
Yeah.
But the explicit mission of this deep dive is to outline a comprehensive solution. How do we actually transition from this reactive nightmare to a proactive strategy? What is the engineered fix?
The fix requires a complete departure from traditional methods. We have to move away from mechanical filtration and embrace restorative engineering. And the primary technological weapon in this new approach is electrostatic oil cleaning, or EOC.
Okay, electrostatic oil cleaning. How does it work? Because you just emphatically told me you cannot filter a dissolved liquid with a physical net.
You can't, so you have to discard the net entirely. EOC does not rely on physical barriers, meshes, or pore sizes. Instead, it operates on the fundamental principles of electromagnetism and Coulomb's law.
Okay, now we're talking physics.
It applies controlled, high-voltage electrostatic fields directly to the flowing hydraulic fluid.
Wait, you're pumping high-voltage electricity directly into a tank of hot hydraulic oil. That sounds like an absolute fire hazard.
I know, it sounds dangerous, but it is completely safe. The voltage is extremely high, often tens of thousands of volts, but the amperage, the actual current, is incredibly low.
Ah, so it doesn't spark.
Exactly. Because there is virtually zero current, there is no heat generation, no risk of sparking, and no risk of ignition. What that intense high-voltage field does is ionize the contaminants. It forces an electrical charge onto every microscopic particle, even the sub-micron varnish precursors that are fully dissolved in the liquid.
So you are magnetizing the liquid varnish, and then what?
Then the ionized fluid is forced to flow between collection plates that hold the exact opposite electrical charge. Because opposite charges attract, the charged varnish molecules are subjected to a massive electrostatic pull.
They get yanked out.
They are physically ripped out of the fluid stream and violently bind to the collection plates. It works regardless of how infinitesimally small the particle is, and it works flawlessly even if the varnish is highly soluble.
It's like sweeping a powerful electromagnet over a sandbox to pull out iron dust. It doesn't matter how fine the dust is, or if you can even see it with the naked eye. the charge finds it.
That is exactly how the physics work. It strips the oxidative contaminants right out of the molecular structure of the oil, purifying it to a state that is often measurably cleaner than brand new virgin oil straight out of the drum.
That's incredible.
And the massive operational advantage here is how the system is deployed on the factory floor. It operates as a mobile kidney loop service.
Kidney loop, meaning it functions exactly like a dialysis machine attached to a human patient.
Precisely. You do not have to shut the massive injection molding machine down to clean the oil. The EOC unit is wheeled up to the machine, the input and output hoses are connected directly to the main reservoir, and it silently draws the oil out, purifies it through the high-voltage electrostatic field, and returns the pristine oil to the tank in a continuous loop.
While the machine is still running.
The factory continues to operate at full capacity, injecting plastic and making money, while the oil is being structurally restored in real time.
That is an incredible piece of engineering.
Right.
But I see a logical gap here.
What's that?
The EOC cleans the oil currently in the tank. But what about the hard varnish that is already precipitated and permanently fused to the internal metal of the servo valves deep inside the machine? The electrostatic field can't reach inside the valve. How do you get the sticky resin off the metal without tearing the machine apart?
That requires the second crucial component of the proactive solution, chemical solubility enhancers. We have to alter the chemistry of the bulk oil to attack the resin. There is a specific highly engineered technology used for this called solvancer.
Okay, so we are dumping chemical additives into the high-pressure system now.
Yes, but we must be extremely surgically precise about what chemicals we are adding. These solubility enhancers are absolutely not surface-active detergents or dispersants.
I thought that was the whole point.
Yeah.
Don't detergents clean things? If my dishes are dirty, I use detergent.
They do clean things, but surface-active detergents and dispersants work by aggressively competing for the surface area of a metal. If you put a heavy detergent into a hydraulic system, it will certainly scrub the varnish off the servo valve.
Oh, problem solved.
But it will simultaneously scrub away that crucial ZDDP anti-wear layer we talked about earlier.
Oh, no.
The detergent molecules fight the zinc molecules for access to the steel. You would successfully solve the sticking valve problem, but you would immediately destroy the pump through massive metal-on-metal friction because you removed its protective shield.
Oh, wow. So you cure the varnish but immediately kill the machine. That is a terrible trade-off. So how do these specialized solubility enhancers work without destroying the critical anti-wear performance?
They are engineered using entirely different molecular mechanics. They are added at a very low concentration, typically just 3 to 5% of the total fluid volume, while the machine is running at full temperature. They are specifically optimized based on polarity, hydrogen bonding, and dispersive forces.
I'm going to need you to translate that chemistry into plain English.
Think of it like a specialized solvent that is chemically tuned to ignore metal and only recognize the molecular signature of the varnish. They do not attack the metal surface. They attack the lattice structure of the resin itself.
Okay, that makes sense.
When the chemically enhanced oil flows over the varnished servo valve, the enhancer reacts with the varnish, breaks its bonds, and chemically dissolves the sticky deposit back into a liquid state. It pulls it completely off the metal and safely back into suspension in the bulk oil.
And once it is dissolved back into the liquid oil, the oil flows back to the reservoir where the kidney loop electrostatic cleaner zaps it with high voltage and removes it from the system entirely.
Precisely. It is an elegant, closed-loop solution. This is the very definition of restorative engineering. You aren't just reacting to failure, buying replacement parts, and changing out degraded fluids over and over.
Right.
You are actively restoring the internal chemical environment of the machine so that the physical parts stop breaking in the first place. You are curing the disease at the molecular level.
Okay, this combination of EOC and solubility enhancers sounds like the silver bullet the industry needs. But if I am the plant manager, I still need visibility. I need a dashboard. I can't just throw high-voltage electricity and specialized chemicals at a machine and blindly hope it works.
You definitely need diagnostics.
Right, because if we prove that the standard oil analysis tests the elemental spectroscopy and the acid number are lying to me, what are the actual right tests? How do I actively monitor the health of this fluid proactively so I know when to intervene?
The transition to proactive health requires a transition to advanced diagnostics. Your maintenance team needs to demand very specific condition monitoring tests from the laboratory. You must stop asking for reactive acid numbers and start asking for tests that measure oxidative degradation potential.
What's the first one?
The first critical diagnostic tool is the ruler test.
Ruler. I'm assuming that is an acronym. What does it stand for, and how does the physics of it work?
RULER stands for Remaining Useful Life Evaluation Routine. The official technical standard is ASTM D6971, and it relies on a complex electrochemical process called voltammetry.
Voltammetry. Again, sounds electrical.
It is entirely electrical. Remember how we discussed that the acid number only spikes after all the protective antioxidants in the oil are completely dead and depleted?
Yeah, when it's too late.
The RULER test is designed so you never reach that point. It measures the actual antioxidant health of the fluid directly. It does this by applying a steadily varying voltage to the oil sample and measuring the resulting electrical current.
How does varying the voltage tell you anything about an antioxidant's lifespan?
Because of redox reactions, oxidation and reduction, different antioxidant molecules like phenols or amines will oxidize and release electrons at very specific predictable voltage levels.
Okay.
By sweeping the voltage across the spectrum and reading the peaks in the electrical current, the RULER test identifies exactly which antioxidants are present and exactly how much of them remains structurally intact. It maps the electrical signature of the oil's defense system.
So it acts like a precise digital fuel gauge for the oil's immune system. It tells you how much of the oil's defense system is left before it starts forming acid.
Exactly. It is a true, actionable leading indicator. If the RULER test shows your primary antioxidants have dropped from 100% down to 20%, you know with absolute certainty that you must intervene.
Like add solvancer.
Perhaps by adding a fresh dose of solubility enhancer, yes, long before the machine ever experiences a single moment of violent chatter. You predict the failure.
Okay, that handles the defense system.
Yeah.
What is the second advanced test?
The second test determines the actual physical propensity of the fluid to form varnish right now. It is called the MPC test, or membrane patch colorimetry. The standard for this is ASTM D7843.
Membrane patch colorimetry. Colorimetry, so we are diagnosing the machine by measuring color.
Yes. The laboratory takes a precise sample of your hydraulic oil and mixes it with a highly aggressive solvent. This solvent forces all of the dissolved microscopic varnish precursors out of suspension and turns them back into solid particles.
Right.
Then they use a vacuum to pull that entire mixture through a very fine, bright white nitrocellulose membrane patch. All of the forced out varnish gets trapped directly on the surface of the white patch.
And then they just look at what color the patch turned.
It is far more precise than just looking at it. They use a digital spectrophotometer to measure exactly how much light is absorbed and reflected by the stain on the patch. They report the result using a standardized metric called the CIE Lab Delta E scale. It provides a precise mathematical measurement of color difference.
So a perfectly clean oil leaves a pristine white patch, and a heavily degraded oil leaves a dark, muddy stain. What are the specific delta E numbers a plant manager should be looking for to know if they are in danger?
A delta E result of 9 or below is considered completely acceptable. The oil is clean and stable. Once the score creeps over 30, it warrants immediate proactive attention. Varnish is actively accumulating in the system.
And what's the worst case?
If the score hits 50 or above, the system is in critical, catastrophic condition.
Going back to that real-world scenario, the case study for machine 15, the one where the plant manager got the green standard report, but the servo valves seized anyway, what was their MPC score?
Their MPC score was a staggering 61.
Wow.
The standard test told them everything was perfectly fine, but the patch was completely dark brown. The MPC test revealed massive critical varnish potential that the other tests were blind to. If that plant manager had been running routine MPC tests instead of standard spectroscopy, he would have seen the dark patch and known a catastrophic failure was coming months in advance.
So what does this all mean for the listener right now? If someone is listening to this in their office at a manufacturing plant, what is the immediate action item? How do they prove this is happening in their facility today? Because there is a really specific 48-hour actionable validation signal we need to talk about.
This is where we transition from theoretical engineering to immediate, undeniable proof for the executive team. If you need to build the business case, you can execute a 2-step validation process in the next 48 hours.
What's the plan?
Step 1, walk out onto your factory floor and identify your most critical or most problematic injection molding machine. Extract a 100 milliliter sample of the hydraulic fluid from the operating reservoir, send it to a certified lab, and explicitly demand an MPC test.
Do not ask for a standard analysis. Demand the MPC.
Correct. Step 2, while you're waiting those 48 hours for the lab results, pull your historical maintenance logs for that specific machine. Look for sudden, unexpected servo valve replacements or massive spikes in unexplained scrap rates over the last 3 years. Now, cross-reference the dates of those failures against documented periods of elevated factory ambient temperatures. Look at the peak summer months.
Oh, I see where this is going. Because higher ambient room temperature means the shrunken reservoir has an even harder time shedding heat into the air. The thermal bottleneck gets worse.
Exactly. The ambient heat acts as a compounding variable. If you see a cluster of expensive servo valve failures repeatedly occurring during hot summer periods and your MPC patch comes back dark brown with a score over 30, you have absolute mathematical validation.
You proved it.
The thermal degradation of the fluid is the root cause destroying your machines.
That is incredibly powerful. It takes this entire complex discussion about thermodynamics, hydrocracked oils, and sub-micron chemistry and distills it into immediate, undeniable proof that a plant manager can drop directly onto the COO's desk to justify the budget shift.
It completely forces the conversation. The executive team can no longer hide behind the illusion that the oil is just a cheap commodity. The data proves it is the central point of failure.
Okay, so we have established the high-level executive strategy. We have electrostatic cleaning, chemical solubility enhancers, and advanced diagnostics like voltammetry and colorimetry. But I want to move away from the macro executive view and get down to the micro level.
The day-to-day operations.
Exactly. I want to talk about the men and women actually turning wrenches and running the floor. How does this massive shift to proactive fluid health change the daily life of a field maintenance technician?
It fundamentally changes their identity. It transitions them from being reactive, stressed-out firefighters constantly swapping broken parts into proactive architects of machine health. To illustrate this transition, let's look at an incredibly detailed, real-world case study of a massive 500-ton injection molding machine.
And this one was processing ABS polymer, right?
Yeah.
Alkylinitride butadiene styrene. That is a notoriously tough, rigid, highly engineered plastic. It's used in everything from automotive bumpers to structural Lego bricks.
Yes, and because it is so rigid, it requires extremely high heat and massive injection pressure to mold properly. In this specific case study, the technicians were battling a chronic, dangerous problem, severe polymer leakage. The machine was leaking 20 to 100 milliliters of molten ABS plastic per hour.
That sounds like an absolute nightmare. Not only is it a mess, but molten plastic under high pressure is incredibly dangerous to the operators. Where exactly was it leaking from?
The massive leakage occurred right at the junction between the machine's nozzle and the mold's sprue bushing. This is the critical high-pressure transition point where the molten plastic leaves the machine's heating barrel and is forced into heavy steel mold.
And what caused it?
The leakage was a compounded failure caused by severe seal wear, an extreme injection pressure of 150 megapascals, and high ambient factory temperatures.
So the technicians are constantly burning themselves, cleaning up hardened plastic, and the machine is producing constant short shots because all the injection pressure is bleeding out of the leak instead of filling the mold.
It's a lose-lose situation.
How does a proactive, oil health-focused technician solve this mechanical problem? We have a 5-step daily maintenance checklist to break down. Step 1 is visual and geometric inspection.
This step requires intense precision. The technician cannot just glance at the machine as they walk by. They must physically inspect and measure the geometric alignment of the nozzle to the mold.
Because even a tiny shift matters.
The engineering data in the case study notes that even a 0.25 millimeter misalignment, a quarter of a millimeter, which is barely visible to the naked human eye, creates a massive microgap. That tiny gap allows highly viscous molten polymer, driven by 150 megapascals of force, to escape and destroy the seal.
A quarter of a millimeter misalignment causes a catastrophic leak and a factory shutdown. That is wild.
It highlights the extreme, uncompromising tolerances we are dealing with. You cannot guess, you must measure. Step 2 on the proactive checklist is a seal material audit. The technician must verify that the physical seals are actually rated for the intense thermal stress they are enduring.
Instead of just using whatever's in the toolbox?
Right. Standard elastomer seals will degrade, harden, and shatter quickly when exposed to 250 degrees Celsius.
So if standard rubber seals fail, what is the upgrade path?
The proactive technician upgrades the machine to specialized heat-resistant Viton seals, which maintain their structural integrity and flexibility up to 250 degrees Celsius. They prevent the thermal degradation that leads directly to the leak. You stop replacing cheap, blown-out seals every week, and you invest in the correct material science once.
Makes sense. Step 3 on the checklist is pressure calibration. And based on the data, this seems to be the most impactful variable of all.
It is the single most impactful variable they can control. In the case study, the machine was defaulting to an injection pressure of 150 megapascals. The proactive technician utilized advanced software Autodesk mold flow simulations to mathematically identify that the nozzle sprue transition was the point of maximum mechanical pressure and highest leak potential.
So what did they do?
By monitoring and optimizing the process parameters and reducing the injection pressure by just 10 megapascals, dropping it from 150 to 140, they achieved a massive, disproportionate result.
The data says the tiny drop in pressure reduced the polymer leakage rate by 70%, dropping it from 60 milliliters an hour down to a manageable 18 milliliters.
Yeah.
I am marveling at how a tiny 10 megapascal reduction or a microscopic 0.25 millimeter alignment fix is literally the difference between a smooth, profitable shift and a total factory shutdown with plastic spraying everywhere.
That is the very essence of proactive maintenance. It is the absolute mastery of tiny foundational variables. Step 4 on the checklist is environmental monitoring. The technician must rigorously monitor the ambient room temperature and the ventilation around the machine.
Wait, let's connect the dots here. Why does the ambient temperature of the room matter to a massive steel machine running molten plastic at 250 degrees?
It matters deeply because of the thermodynamic bottleneck we discussed at the very beginning of this deep dive. The shrunken hydraulic oil reservoir relies entirely on the ambient air in the factory to shed its immense heat.
Right, the teacup engine.
Exactly. If the room is sweltering, the oil cannot cool down. The fluid degrades faster, the polymer viscosity changes, the varnish precipitates, the servo valves stick, the process drifts, the machine attempts to compensate by violently spiking the pressure, and that pressure spike blows out the seals on the nozzle, causing the ABS leak.
It's all connected.
The ambient environment is directly, causally connected to both the fluid health and the mechanical seal integrity.
It's a massive interconnected chain reaction. The room gets hot, the oil dies, the valve sticks, the pressure spikes, the seal blows, the plastic leaks. It all leads back to the oil. And the final step on the daily checklist is the mold repair protocol. What happens if the failure has already occurred and the leaking molten plastic has scarred or damaged the incredibly expensive steel mold?
The repair process must be meticulous. A technician cannot simply take a chisel and scrape the hardened plastic off the steel. The protocol dictates precise TIG or laser welding to carefully rebuild the microscopic worn areas of the steel, followed by precision machining or milling to restore the exact dimensional tolerances of the sprue.
And the final finishing.
It requires intense, critical polishing. The technician must use specialized stoning, ultrafine sandpaper, and finally diamond paste to restore absolute mirror-like surface smoothness. Any microscopic scratch left behind will create friction, trap plastic, and cause a brand new leak.
And then they oil it.
Finally, the restored mold must be thoroughly coated in a specialized rust-preventative oil before being put back into the production cycle to prevent flash rusting from the ambient humidity.
Honestly, it sounds more like Swiss watchmaking than heavy industrial manufacturing.
It absolutely is, and the economic impact of combining this rigorous daily mechanical checklist with the advanced mold flow simulations and the electrostatic cleaning we discussed earlier is profound.
What's the bottom line?
The case study conclusively notes that by implementing these precise, proactive measures, a factory can boost overall production efficiency by 5% and save thousands of dollars in replacement parts per machine annually.
Which is huge.
When you multiply that savings across a massive plant running 50 or 100 injection molding machines, you are talking about massive, game-changing capital preservation. It turns technicians from reactive firefighters into proactive architects of machine health.
It completely rewrites the financial equation of the entire factory. Well, we have covered an incredible amount of technical ground today. Let's do a quick, comprehensive recap of the journey we just took.
We started by identifying the hidden architectural flaw driving the crisis. OEMs deliberately shrinking hydraulic reservoirs by up to 40% to advertise a smaller physical footprint and faster cycle times, creating a massive thermodynamic bottleneck that fundamentally changed the operating reality of the fluid.
We explored the kinetic energy and chemistry of how that intense, relentless heat creates sub-micron varnish. We saw the temperature paradox, how the varnish remains dissolved and invisible when hot, but precipitates as a destructive, sticky resin the moment it hits the cooler servo valves.
We connected the hysteresis of that sticky valve directly to the destruction of overall equipment effectiveness. We detailed how erratic, unpredictable pressures cause the short shots, the flash, the sink marks, and the warped parts that fill the scrap bins and demand intense manual labor.
We exposed exactly why standard mechanical filters are completely blind to these submicron soluble liquid particles. And we broke down the chemistry of why traditional oil analysis tests like elemental spectroscopy counting dead ZDP atoms and acid numbers masked by hydrocracked group 2 base oils give executives a dangerous false sense of security while the machine destroys itself from the inside out.
And most importantly, we detailed the complete transition to a proactive strategy. We explored deploying electrostatic oil cleaning to physically strip dissolved contaminants using high-voltage fields. We discussed utilizing specialized non-detergent solubility enhancers to dissolve internal resin without destroying anti-wear layers. And we established the necessity of advanced diagnostics like MPC colorimetry and ruler voltammetry tests.
Finally, we brought it down to the factory floor with a rigorous daily technician checklist focusing on microscopic alignments, heat-resistant seal material science, precise pressure calibration, and ambient environmental monitoring to stop the bleeding before it ever starts.
It is a comprehensive, necessary shift from reacting to catastrophic emergency repairs to proactively architecting an oil health strategy at the molecular level.
It has been an absolute master class in systemic engineering. But before we sign off, I know you always like to leave us with a broader concept to chew on. Based on everything we've unpacked today about this massive multi-million-dollar blind spot hidden inside heavy industry, what is the final provocative thought you want to leave the listener with?
I want you to step back and consider the psychology of maintenance and capital we've discussed today. We've seen how an entire global industry passively accepted that hydraulic fluid, the very lifeblood of the factory, the medium transferring immense violent power, was just a cheap disposable commodity rather than a highly engineered structural asset.
Right.
That single false assumption cost them millions in scrap, downtime, and replacement parts. So I leave you with this question to explore in your own world. If an entire industry of brilliant engineers can be completely blind to the catastrophic systemic failure of its most critical fluid, what other consumables in your supply chain are hiding systemic design flaws? What else are you routinely replacing, constantly fixing, and writing off as a normal, unavoidable expense that shouldn't actually be breaking at all?
That is a phenomenal, unsettling question. Are we just accepting chronic failure because we fundamentally misunderstand the asset? Well, thank you all for joining us on this deep dive into the hidden world of hydraulic varnish, thermodynamic bottlenecks, and restorative engineering. Our mission is always to shortcut your path to being brilliantly well-informed, and I think we definitely achieved that today. Until next time, keep questioning the baseline and look much closer at the things you take for granted.